the same guideline which was basically proposed by Mononobe Okabe, Japanese scientist. Based on that, these particular things are going on. If you see the basic concept, if you see the static design and the seismic design, the difference between these two is that we have to consider the additional forces coming attributed because of the seismic forces. Now the condition is that seismic force, how we are going to consider. The present code suggests the equivalent static loading. For a seismic signal, for an earthquake acceleration, we have acceleration in horizontal direction. We are generally recording the vertical direction. So here you can find, here next slide, obviously you can find very easily, you can see W into KH and W into KV. These two components of forces are being taken into consideration. KH means the horizontal acceleration coefficient and KV means vertical coefficient. Multiplied by the W means mass, weight of the soil, and this mass into acceleration gives you the inertial forces, which is acting in the lateral direction. The thing is that number of school of thoughts are there. Equivalent static forces, you can do the design, which we are considering in our present code. Lot of developments are there. Pseudodynamic forces somebody is taking, and you can also do a design based on the actual dynamic condition. Based on the actual dynamic condition, time history analysis, all these things. So we are not going into deep into that. Present codal understanding is that we are going to consider the equivalent forces, equivalent static forces of the dynamic force, the earthquake forces, to be in the safer side. Guideline was given, and with the help of this, coefficient forces, we are adding up in the design of the active and passive earth pressure for the seismic condition. That's the point of saying. But at the same time, code has not introduced this part now, but coming days it will be introduced, the displacement oriented design. Because in seismic design, presently we are being occupied with this force-based design, but at the same time, we need to have some check of the displacement also, because in seismic failures, it is observed the retaining wall has been failed, not by the force, because of significant distortion or displacement. So that was the point. Hopefully, coming days, code will be addressing these things. Now, this is all of you know that the stabilities under three conditions, we are going to check the stability of any retaining wall. Obviously, this example is highlighting about the traditional retaining walls, the rigid retaining walls. The external stability we used to check. First is sliding category, overturning category, bearing capacity failure, and the overall failure. These four checks we used to do for any kind of retaining wall. I'm not going too deep into this. These are some, this is obviously all of you know, factor of safety we are assessing based on these two factors. One is resistive force, another is the, obviously the driving force. This factor, we have a guideline, how much we have to ensure for a safe design. So this is for the sliding, this is for the overturning, and this is for the bearing failure, right? I'm not going into deep because all of you know these things. These are all textbook materials. Now, these are all bearing capacity, how to check all these things in a slide. Now, it is see, this is a failure arch when you are checking the bearing capacity failure check. Because around this arch, this is the critical zone where you need to assess the forces categorically to assess the stability of the wall. Now, this additional stability check also, internal stability. What is this? This internal stability is basically, if you see, it's a long-standing wall, and because of this pressure, a huge amount of bending moment is coming at the stem part of the wall. That you have to check whether this particular stress is being overtopping the flexural capacity of the stem material or section of it. That is also called as the internal stability. Sometimes we miss it. That may lead to a structural failure of the stability, right? Now, coming to the practical cases, we have tried to jot down, I have tried to jot down some of the classical failures in some of the sites, in particularly in the Northeast India. I belong from Northeast India, Tripura. So from the newspaper and the website, I've tried to find out these particular photographs where number of casualties has occurred, as well as infrastructural damage also occurred mainly during the rain-induced landslides. This is practically a very important phenomena where the standing retaining walls, the I mean, rigid retaining walls has been failed significantly, not only this part, around the world we can see. Now, what is the conclusion? What is the message coming to this, to the today's society or to the designers of today's, how to address this issue? That's why we have collated this particular figure. Now, types of retaining wall already I have discussed. A long variety of retaining walls are there. Flexible retaining wall, broadly if you specify, and the rigid retaining walls. So I'm not going into this part, already you are introduced. Now the question is that the currently you can see flexible retaining wall, variety of flexible retaining walls are coming into the picture. I will address the questions, I think, later part. Okay. Now quickly let me complete. So here in this slide is basically representing the old and new retaining wall system. The older system, what are the drawbacks, and the new things, what are the advantages? Basically, these new technologies we are bringing to address the shortcomings of the old retaining walls, at the same time keeping the mandate of the sustainability concern. That's why you can see sustainable goal. So quickly I can show you the presently the flexible retaining walls. What are the benefits? From this figure you can at least categorize the basic figure. You can see the left hand side diagram, the right of way. If you're constructing a rigid retaining wall, the conventional retaining wall in a slope, you can see the right of way you are getting for a car to move. The rest of the part you cannot use because some of the cutting section will be there, some will be filling section. Now in the bottom figure in the left hand side B, you can see the right of way can be extended up to a significant depth, significant width. You just see two cars can pass through it if you adopt the flexible retaining system. Obviously, you can see here MSE wall, mechanically stabilized wall, at the same time followed by some what is called nailed walls. So these are all coming under the flexible retaining walls, or the currently last few decades this has been discussed, developed based on the current challenges. Now, what are the challenges for the conventional walls? Soil pressure is obviously a challenge. Hydrostatic pressure due to poor drainage, weak or unstable foundation soil, inadequate design or construction or degradation of the materials, weathering, freeze-thaw cycles and vegetation growth, etc., seismic activity, surcharge loads, and so on. Number of challenges. We have categorized the traditional retaining walls, which need to be addressed by these new innovative retaining walls. Now, this particular actually slide I made, actually I found this is very useful because one research paper they found 4 variety of retaining walls they have considered based on the sustainability aspect. What are these 4? The first one is being categorized as R1, which is basically Gabion wall. All of you have a little bit idea. I think Gabion wall, these are nothing but meshed, I think rubbles is being meshed, and it's almost equal to a gravity wall, the past gravity wall. Now the concept is that this Gabion wall. Then second one is the creep wall. Third one is the rubble masonry wall, and the fourth one is the counterfort retaining wall, the traditional wall. Now, what this particular study, what they did, they used to find out the sustainable merits. That means life cycle assessment from the point of view of environmental factors as well as the economical factors. I'm just coming to the conclusive part is that they have considered when the life cycle assessment was done, global warming potential, human toxicity potential, then acidity potential, FDP, that is forensic damage potential. Number of life cycle assessment factor was considered, and interestingly found that the R1, the Gabion type of wall, is giving the advantageous wall, which basically address the sustainability in a better manner, considering these both the aspects, environmental as well as economical. So that was the abstract from this. So keeping beyond this fact, we can see how these mechanically stabilized retaining walls, not always Gabion walls, some other materials are being used, how it looks like, how it has been stacked, and how the geograde geosynthetics are being applied, how is mechanically synthesized, at the same time drainage layer is being provided. So this is the schematic diagram. Now I'm jumping to the Gabion wall, and I will suggest every learned audiences to go through IRC SP 1162018, where it states about the different types of Gabion wall. The point is that in this particular slide, you can see this is a Gavian fascia. The fascia is made up by the Gavian wall and which is being strengthened, horizontally strengthened by use of geogrid. Now in Gavian walls, you can see use of non-open geotextile in the right side, and as well as the proper drainage system you can provide. And the design concept is that the design is concept by the traditional, we are considering for gravity wall, retaining wall now, that design is being considered. So this is the design. I'm not going into these details. That is followed by the traditional gravity wall design. Along with this, some particular drainage condition has been addressed. Now, this is the different failure condition of the Gabion wall, failure mechanism, overall failure, failure of the foundation bearing capacity, already you know, sliding failure, overturning failure, then one additional failure is there, internal failure. So all these failures you need to address, and you can see in the left-hand side, the forces pattern will be almost same as traditional gravity wall. Okay. Now here see types of gravity retaining wall. The advantage of this gravity retaining wall is that I will be sharing one case study which we dealt in Tripura, that when you are designing such gravity retaining wall, the gravity retaining wall can be acted as a retaining wall. At the same time, this retaining wall beneath this, you can see in the left hand side that a mattress can be given for erosion of the river. That is flood protection embankment. How can you give both erosion control at the same time retaining wall system? So this is having a very good merit from the point of view of earth erosion control embankment, I mean flood protecting river embankments. Now quickly, advantages of quick Gabion wall. I'm not reading: durability, strength, drainage, cost effective, easy installation, environmental benefits, low maintenance, and so on. Now case studies, I'm entering to the in general. These are the some of the example photographs taken from different cases. I have just written all these things. For example, the first one is the Hathani River Protection Area is made by Gabion walls. These are all Gabion walls construction of different dimension, different specifications. Next is coming mechanically stabilized retaining wall. Just I was just mentioning, with Gabion wall or any other fascia material, if you're using geotextile or any other metallic sheets for reinforcing, that is the example of mechanically stabilized earthen wall. Now it is for geocell retaining wall. This is classically very interesting, and very recently, I think past decades, his work is going on geocell. So it is very sustainable thing, and as well as is a flexibly potential, sustainable, all the merits of this. So this work is going on in our country also, and several case studies has been reported. Now, as I was telling, I was just sharing with the first of all the case study, flood protection Howrah Earthen embankment in Tripura. Actually, this particular project was dealt by me as a principal of investigator. I would like to stay some time to make you show you how we have dealt this case and where we have suggested the retaining wall design. Now, this is the snapshot of the this is the satellitic snapshot of the river Howrah, which is passing through Tripura, Agartala, I mean the capital of Agartala, and it is going to Bangladesh. So we have done a thorough soil investigation for the part of the flood embankment jurisdiction. Around 6 kilometers was given. Smart city project are going to be constructed, and right now it is almost constructed. I'm just sharing, I think during COVID pandemic time, we dealt this case. During pandemic time, we performed the health assessment of this flood protecting embankment of Howrah River. So quickly just showing you some of the snapshot of this flood protecting embankment. Already people have constructed road is there, and beside the road, a significant agglomeration is there. I mean, civic bodies are there, houses are there. Any kind of breach of this particular embankment will cause significant casualty around Agartala. This was basically, this particular embankment was made during the kingdom period, Raja, in the year of 1800s. Now it is around, you can understand, it has passed more than 100 years. This particular embankment needs a health assessment for Smart City Mission project. So these are the smart snapshots of the cross sections developed taking the bathymetry survey. Now we have done several investigations, geotechnical investigation, to assess the subsoil strata as well as the geotechnical properties at different cross sections. Now, after this, we perform the analysis, numerical analysis in GeoStudio, and I'm not going to discuss about the every steps on GeoStudio. Finally, we found out the critical sections where we need some strengthening from the point of view of seepage failure, from the point of view of seismic condition, from the point of view of rapid sudden drawdown, from the point of view of, rainfall condition. All these critical condition we have considered. We have assessed the stability of the slopes at various particular conditions, and we finally come down the critical sections where some retaining system to be developed. So accordingly, we have finalized and we have given a proposal to the body that this is the factor of safety at different conditions. Critical rural condition, you can see steady seepage, rapid drawdown, rainfall infiltration under different conditions. The factor of safety are reporting. We are getting very good factor of safety in several locations, but in few locations we got some. So what is the solution we have given? We have given a solution of berm construction, and as I was telling about the mattress, Gabion mattress, as well as the Gabion retaining wall in a composite form to be installed over there. And I can show you some of the photographs. What is the present condition? As per our suggestion, they have got the approval of the project. This is the present condition where the Gabion walls are being constructed across along the river, and mattress is also being given at the beach. That is already specified in the SP special publications. This is another case study. We are just now dealing with these things. So I thought that why not we should share. This is a very simple case study. Central Warehouse Corporation are going to install a plant at Shabroom. There's a huge plant. You know, all of you, Central Warehouse Corporation, they're constructing, they're basically storing a warehouse, through a warehouse, lot of products coming from export import, right? So what we found, whatever the construction was made, they have not made any significant arrangement for the lateral retaining wall adjacent to the building. And after a recent rain, incessant rain, they found the red mud field of soil has been washed away, and the building is in endangered condition. So we rushed to the site, and we have suggested some of the guidelines. Presently, the work is going on, and we are currently designing a Gabion wall because there is some front shortage, front crunch was there, and we are going to finalize this particular thing through a Gabion wall. We're going to design based on the subsoil strata that how we can give in economical manner in the safety to this particular void, because a considerable load will be coming. Highly loaded truck, about 25 ton will be coming through this backfill material. So it's a challenging thing. So you have designed a Gabion wall up to a certain depth, and rest of the parts soil will be improving by some ground improvement techniques so that this can be used for the traffic load. So this part I'm skipping, soil nailing. I think Dr. Mahajan will be talking. He's the expert on this. Nailing also a potential technique of retaining wall system out of this flexible system for Northeast India category, because this involves less inconvenience for the traffic. This particular technique is being very easily can be applied without making inconvenience to the traffic. You can understand in Northeast India, if you make an inconvenience, then it will be detached from the mainstream, and there you can understand the after effect and the implications. So this technique can be also very prudently can be practiced in this part. So I'm just skipping because of the time paucity. I understand already. My time is already almost in the. So this is the different stages. Design techniques. I hope sir will be mentioning this thing. Failure mechanisms of nailing techniques, nails. What are the stress distribution? So these are the things I would like to skip. I will share if you need the slides. So this, I'm going to this is my slide. What the message at this moment we are going to give for the country as well as the world, for particularly from the point of view of retaining wall construction. Sustainable, economical, availability, waste management, eco-friendly. That means we are going to meet up the sustainable goals for future development. So that is our current motto. With this objective, we should design the retaining wall, the flexible retaining wall, or the hybrid retaining wall, or other way you can say composite retaining wall, keeping view on these factors. So currently research is going on. I'm not going to in a current position to showcase the results. It is in investigation stage. We are going to design some kind of composite retaining wall which meets the sustainability goals. With this, these are some of the salient references presented over here. Thank you for your patient hearing and giving me an opportunity to speak in this platform and have a chance. Thank you. Jai Hind. So from my side, I'm just, for any queries, we can get back after the session. Is it fine from my side, sir?
Thank you,
Are you
Dr.
with me?
Saha. Thank you for the nice presentation that we had. As Dr. Saha already said that we'll be taking the Q&A session for both session after the second presentation. So moving on now, I would like to invite Dr. Ratnakar R. Mahajan. Dr. Mahajan is alumnus of IIT Bombay and working as Regional Technical Manager at McAfee, responsible for India, Southeast Asia, and Pacific markets. He is a civil engineer with key experience in soil reinforcement, ground improvement, retaining structures, slope stability, river training, channel lining, and rockfall protections. Now I would like to invite Dr. Ratnakar. Yeah.
Yeah. Very good afternoon to all. Sumit, I hope I am audible.
Loud and clear, sir. Yes. Yeah.
Yeah. Okay. So let me share my screen. So before I start, I would like to thank Mr. Tanmay Chakraborty from Institute of Engineers, who had thought of this webinar series. And of course, thanks to Professor Rajiv Saha, who agreed for sharing his expertise on this topic when we have requested him. So, and he made my life very easy because he has covered most of the basic things what I wanted to cover. And Professor will agree, repetition is the best way of learning. So probably there will be many things which I will be repeating, but I think the audience will get benefited from that in the sense the details will be very much similar. At the start, I would like to just introduce about the company I am coming from. So basically, I am working in a company named McAfee, which is present all across the globe in all 5 continents, with let's say manufacturing around 23 locations, having an employee base of more than 3,000. In India, we have been incorporated in 1998 with our corporate office at NCR region in Gurgaon, with our subsidiary in Nepal, which started in 1995. Now, coming to today's topic, there are various types of retaining walls. I would say the conventional retaining walls, which are typically dry stone walls, random rubber masonry, UCR walls, Gabion walls, RCC wall, sheet pile walls, anchored walls, screed walls. So most of these retaining walls are very rigid, except maybe the Gabion wall. Now these rigid retaining walls, they have some drawbacks. The drawbacks are basically the failure will often occur in the rigid structures when there is a movement of water. So because of movement of water, you have a lot of stresses that's being generated in the soil, especially the pore water pressure will increase, and finally the failure will be observed. Compared to the other retaining type of walls, the rigid walls are basically very, very expensive. Just a minute, I am getting a lot of noise from backside. I will just close the window. Yeah, sorry for that. Yeah. So the next point is basically very important part is the time required for construction. Nowadays, what is required is a very fast space the construction to be done. Also, it is expected it has to be economical. Very important thing when we are working with these rigid walls, of course, we are looking at the differential settlements. For example, Professor Rajiv Saha has showed various failures, especially in Northeast region during monsoon. So there are movements, but these movements cannot be tolerated by the hard solutions. So if we have to classify let's say the retaining structures, we can classify them. The first one is a load support mechanism, that is based whether earth retaining structure is stabilized externally or internally. Externally stabilized walls use external structure that prevents the backfill from sliding or any other potential failure. One example are modular gravity walls like Gabion walls. Internally stabilized walls are reinforcements installed within the soil mass. The second criteria is the construction concept, so fill or cut situation. Third is the system rigidity. A rigid earth retaining structure does not experience bending deformations, while a flexible earth retaining structures can be subjected to rotation, translation, but also experiences bending deformation. Last one is the service life. We design temporary earth retaining structures when the service life is less than 5 years, or permanent structures when design life is more than 5 years, usually 75 to 100 years. So to start with, let's look at the modular gravity walls. That's the Gabion. Professor has already covered most of the things, but I will take you a little deeper in the Gabions itself. Let's look at what are the types of Gabions. Gabions are made with various materials, like the first one, what you see is the double twisted hexagonal wire mesh, where material is steel, and this hexagonal mesh can be made by machine or hand. The second one, what you see is a single twist mesh, which is used to make the Gabion again. The base material is steel, and again it is made by machine or hand. The third one is the welded one, where the material is steel, and basically it is welding is done by a machine. The fourth one is basically made with the polypropylene, that is a polymer, is a U1 material, and they are handmade, and they are suited typically only underwater. They cannot be used when they are exposed to the sunlight. All of these, usually the double twisted hexagonal Gabions, are the one of the best when they are observed for any kind of situation, let it be dry, wet, or changing situations. Typically, when we look at the Gabion wall, the components are, of course, the Gabion itself. Second is the backfill soil which is placed at the back of it. Then most important part is a filter, because the Gabions are porous materials. In the photograph, you can see there are voids between the stones, and the possibility of the backfill is getting washed is there. To avoid that, a non-one geodexide is placed at the back of Gabion, which act as a filtration and drainage material. And then, of course, the filling material inside the Gabion itself. So the Gabions are nothing but rectangular cages. They are made with one steel wire mesh filled with stones. This forms basically the blocks for the retention work or protection works. These boxes are typically have the mesh all around. So which are typically, you have side panels, you have the top and bottom panel, you have diaphragms. So diaphragms are nothing but the vertical panels in the middle of the box. Lacing is a wire which is used to join the lead with the side panels, and the selvage and edge wires. These are the typical components of the Gabion. Now, when we talk of double twisted hexagonal steel wire mesh, there are many kinds of double twisted wire mesh that are manufactured combining different diameters of wires. So like the mesh openings can be 6 by 8, 8 by 10, or 10 by 12. The shape remains same, that is hexagonal. There is a double twist. The advantage of double twist is by accidentally, even if you break one of the wire, the mesh doesn't open up. It doesn't unravel, and the integrity of the mesh is maintained. And hexagonal shape is one of the best shape where you can find the load distribution, especially in tension, is very good when you have such a shape. Typically, the wire used for this making of Gabion is steel wire. Typically, we call it as a mild steel wire, high elongation wire, where the tensile strength could be 350 to 550 megapascals. And this wire is usually protected with a metallic coating, for typically a zinc or a zinc aluminum alloy. We call it as a metallic coating for the protection from the corrosion. And on top of that, additionally, a polymeric coating, typically a 0.5 millimeter nominal thickness, is provided, which is either PVC or a polymac material. So this polymeric coating again improves the design life of the gabions. These gabions, they come in a different form. So let's look in this figure where we're talking of a length, width, and height. Typically, the height of the gabions is 0.5 meter or 1 meter. The length is usually 2, 3, and 4, and basically sometimes even 1.5 also. But typically 1.5 meter high gabions are usually 1 meter wide and 1 meter height. 1.5 meter gabions doesn't come with a 0.5 meter height. So with these different sizes, you can really make a structure which can be properly designed. Now, the fill material usually in these gabions is a rock fill. There are certain requirements in terms of the filling of this material or the specifications of this filling material. The size of the stone is usually governed by the mesh opening. So you shall not have the stones which are very small than the mesh opening, otherwise the stones will come out. You cannot have very big stone size, otherwise there will be very low basically density will be achieved. Typically it's 1.5 to 2.5 times the mesh opening is the typical requirement. And the tolerance on the stone is usually plus minus 5%. It is expected that the specific gravity of the stones could be around 2.3 to 2.6 or 2.7. The stones shall have sufficient durability. So let's say Los Angeles average value shall not be more than 45. The geotextile which is used at the back of the gabion wall for the filtration and drainage purpose is typically recommended as a non-woven geotextile, which basically separates the fill from the gabion and acts as a filter material. It can be made with either polyester or polypropylene, and usually this geotextile comes in a roll form. Now, design steps, Professor has already explained many of the things, but I will just quickly glance through the certain design modes. Typically what we talk of, the starting from overall failure to bearing capacity, sliding of the gabion whole wall as it is, overturning, or most important part, internal failure. Many of the designers are not aware of the internal failures. So first we need to understand the earth pressure. Typically you can look at the retaining wall cross section where you have the lateral earth pressure which is acting on the wall. And this could be typically, as Professor explained, we can look in the active state, passive state, or at rest. The earth pressure concept is based on theories related to the active and passive state of the soil that changes due to the movement of wall. It is not easy thing to explain. At least I would say, what Professor explained, I cannot explain that simpler way. So usually the retaining walls are designed with the active state condition. That's the recommended practice. So what is this active thrust? Let's look at it. So you have a retaining wall, you have soil. So for now, let us accept that when we have a wall holding a mass of soil, this soil produces a pressure against the wall, and this pressure, in this case, it is resulted only by the weight of the soil column. So we can say that higher the wall, the bigger the earth pressure. It is very easy to understand that when we talk about vertical pressure. So let's look at when we want to look at the active thrust. Let's understand what is the vertical pressure, which is the density of the soil into the height, which is the typical vertical pressure. Now you can relate this vertical pressure, convert it into the lateral pressure by applying a constant that is typically called as the K, earth pressure coefficient. For active state it is Ka, for passive state it is Kp. Now earth pressure coefficient basically let's say can be decided based on these two researchers. The Rankine method is very simple and can be done without any software and sometimes without a calculator machine, and that's why it is so important and why it's taught on the university. can be used pre-designed, and to determine the passive thrust. Let's say you want to determine passive thrust or active thrust, you can use the software GavaQueen to calculate the passive thrust by Rankine's method. The method developed for Rankine has some limitation, and because of that, the engineers has to use other methods, and that is here enters the Coulomb's method. So the reason why Coulomb's method is it is so important for us, it is because he consider inclined wall soil surface, not the vertical, and at an angle active earth thrust application, that is delta, based on the roughness of the surface. The Rankine method does not consider these 2 points, and these makes a lot of difference in the Gabion projects. Then how do we consider the effect of phreatic surface? The presence of phreatic surface in the retained soil mass will increase the active thrust, and of course you need to model it properly, and accordingly you need to consider the unit weight of the soil, whether submerged or dry or saturated. Of course, when you design these retaining walls, loadings on the backfills are added to the weight of the soil wedge, assuming the loads are acting directly on the wedge itself. Now, when we look at the free body diagram, of course, you can have active pressure, the passive pressure in front of the wall, the mass of the Gabion wall, that is the W itself, and then you have the resultant forces, typically a normal force at the base N, and the tangent force or the lateral force, that's the, let's say, TD. And when you take the ratio of stabilizing force to the sliding force, you will get a factor of safety against sliding mode of failure. When you take movement of all these forces at the toe of the structure, there will be clockwise movement, anti-clockwise movements. So, of course, the stabilizing movements, which are nothing but clockwise movements in this figure, what you see, and overturning will be the anti-clockwise movement. Now, if you take the moment of stabilizing ratio of the stabilizing moment ms by mi, that is, you will get a factor of safety against the overturning. When it comes to the foundation design, the bearing pressure comes an important part, where you need to calculate the resultant force, the vertical force, that is the N, and you need to make sure the wall is having a sufficient wide base so that the resultant lies in the middle third rule. This is basically following the Meyerhoff's theory. So for that, of course, you can calculate the eccentricity by basically taking a ratio of resisting moments minus overturning divided by the normal force. And then you need to calculate the basically factor of safety against the global slip failure, which can be analyzed by limit equilibrium method, where there are different methods available like Bishop, Janboos, Morgeson-Price, Swedish circle method. Typically, Bishop's method is very commonly used because it is very simplistic method which ignores the interslice shear forces, as well as the interslice forces. However, it relies only on the moment equilibrium, and finally, the factor of safety arrived from the Bishop's method is not so far from the other methods. So Bishop's method is generally used for the slip surface. The important part I mentioned is internal stability, which is very rarely known and people don't do this, but it is recommended you check the internal stability. What is internal stability? At each layer of Gabion, you need to check the basically compression and shear based on the forces coming on that. For that, of course, you need to understand the behavior of the Gabion under the compression, behavior of Gabion under the shear, and how the mesh, because this is a interaction of a stone fill and the mesh, how they interact together and how do you model. Basically, for shear force, you calculate the T by V, where V is the width and force, and the compressive stress is N by 2D, where N is your normal force and D is the location. Now, the stones have the angle of internal flexion. Let's say it can be 45 degrees. And the effect of mesh can be quantified in terms of the cohesion. So we have done extensive research around 30 years back, and recently we have conducted another research basically on compression and shear testing, and we have arrived with these compression shear parameters, and then we have come up with a design method now which can take care of even the predicting the movements of the Gabion walls. When we design these retaining walls, as professor mentioned, you can refer IRCSP 116, which gives what are the different factors of safeties for different modes of failure. You can just refer this and design the wall. Now, while you design the this Gabion wall, you need to keep some points in mind. If you can see, the walls, the Gabion walls can be stepped outside or stepped inside. Usually Gabion wall steps outside are preferable because they can be constructed on a horizontal ground. When you construct these Gabion walls stepped inside, you will require to provide a batter of 6 degrees. If you see the figure shown at the bottom, avoid irregular wear surfaces, like you have some Gabions projecting out from its location in vertical plane. Don't follow this kind of soft design. Or sometimes people just stack the Gabions one top of each other on a slope and say this is a Gabion wall, but this is not the Gabion wall. The wall configuration like this one shall be checked against the slope stability and not as a conventional retaining wall, because this is not the conventional retaining wall. Secondly, when you use the geodetic style, it's a dry situation, you can provide basically the geodetic style at the back of the wall. Avoid placing the geodetic style at the base of the wall. When you have the free water surface, then of course you need to take care of the water levels. Usually the water levels shall be lower than the wall height, and check the water profile data when you enter in the design part of it. When you do overall stability checks, of course, you need to take care of modeling it properly. Sometimes, those who practice the conventional types of retaining walls may suggest even kind of shear keys, but in Gabions, you don't require this kind of shear keys, or they may recommend to provide a very big founding layer. Even that's not really required. It's typically, if you draw a 45-degree line from the heel or toe, whatever the line is going to cut at the boss Gabion, that Gabion is going to be effective. Beyond this portion, it's not going to be effective. Sometimes you may use the Gabions as additional foundation if there are the scouring expected. In case you want to optimize the depth of foundation, you can provide the matrices in front as taking care of the scar. Now, these Gabions can be used at various locations. So it could be landscape and architecture, it could be hydraulic works, including the rivers, canals, or even coastal. They can be used like as I said, for coastal protection or marine structures, safety noise barriers, or retaining walls itself. There are various codal provisions available. Just for your information, of course, for design and installation, you can refer IRCSP 116. For the material specification, you can refer IS 16014. Recently, the Bureau of Indian Standard has issued a circular that the Gabions which are manufactured and used in the projects must be BIS certified. So, for example, if you use a helmet while riding the bike, you will find ISI logo at the back. Similarly, now it is mandatory to use this Gabions only BIS certified. Then IS 14458, which is basically related to the design of retaining walls for hill area. So there are 10 different parts of this document which talks of various types of retaining walls. IRC 89, which talks of river training. It also mentions the use of this Gabion wall, MRTS different sections. IRCSP 113, which talks of flood disaster mitigation. That also mentioned this technology. IS 34, which is basically recommendations for road construction in areas affected to waterlogging, flooding, salt infestation, and IRC 56, recommended practice for treatment of embankment and roadside for slope erosion. One of the important part, we need to understand the carbon footprint. So we did just one analysis of, let's say, a Gabion wall versus, let's say, a conventional concrete retaining wall. So the graph shows the emissions of CO2, basically comparing the retaining walls, that is of the concrete, versus the Gabion walls. Of course, for concrete retaining wall, you require the cement, the steel, the aggregate, the sand, and in Gabions, you require the mesh plus the stone. So here the varying factor is basically the stone, from what distance you are going to quarry, whether it is going to be less than 100-kilometer distance or more than 100-kilometer. And when you see this comparison, you will see that the Gabions can reduce almost 80% of the CO2 emissions. And India has committed 2070 to be a net zero. That's our target. So if we have to go in this direction, then we need to adopt the solutions which emit very, very low carbon. Now, the next types of retaining walls, what we have seen is the, let's say, internally stabilized, in that you have reinforced soil walls. So again, we will look at this chart. So we are talking of internally stabilized walls where the reinforced soil fills. They are reinforced with metallic or polymeric reinforcing strips or grids or sheets. So the reinforced soil wall is not new to the mankind. In the photograph, you can see the structure around 1500 BC, which was originally 87 meter high, now is 45 meter high. This is like Jugagot of Akbar, where the soil is used with the natural reinforcement. Another example is the Great Wall of China, 2006 BC. And in India, we know reinforced soil for even before that. If you see the old houses, what are built in the rural areas, typically mud houses, where we will use a local vegetation and build houses. That's nothing but the reinforced soil concept. To make it simpler, if we have to understand the reinforced soil from, let's say, a scientific approach, let's look at this box with these volunteers. The box, the front one is side panel can be removed. Let's take a drawing sheet, the white color drawing sheet, and let's have the paper strips cut from, let's say, another sheet. Attach these paper sheets to the drawing sheet, and let's put the drawing sheet in the box on the front panel, which is removable. Pour the sand and then place the strips, pour the sand, place the strips, compact it. You can compact yourself as walking over it, or use a mallet, or small compactor. And later on, if you remove this front portion of the box, you will find the drawing paper and the paper strips are able to hold the soil completely vertically. Otherwise, it would have been at an angle, which is angle of repose. And even on this small retaining wall, there is an additional structure that's being placed. And you can see the wall is completely, the sheet along with the paper strips is completely holding the soil mass. How it's possible? Of course, it is possible because of the interaction of the soil and the paper strips, So the forces from the soil are transferred to the paper strip through friction. Now, this kind of reinforcements are typically, named as soil reinforcement, typically referred as the geosynthetics. Geosynthetics are planar products manufactured from polymeric materials used with soil, rock, earth, or other geotechnical related materials as an integral part of a civil engineering project, structure, or system. So the raw material could be steel, fiberglass, it could be polymers or natural materials. Now, many a times you might have seen that generally speaking, the earth retaining structure is a structure that retains soil and prevents it from sliding or eroding away. These structures are generally used for vertical slope stabilization and to minimize the right-of-way requirements, solving the space constraint problem. For this reason, this system represents important solution in highways, railways, bridge abutments, wing walls, Over last more than 2 decades, these reinforced soil wall or mechanically stabilized earth wall systems have replaced traditional cast-in-place concrete retaining walls, mostly because they are installed easily and quickly, but also because flexibility and high seismic loads. And how do we differentiate between the wall and slope? Basically, when you have angle less than 70 degrees, you refer it as a slope. And when you have angle greater than 70 degrees up to 90 degrees, you refer it as a wall. And wall is further classified as vertical walls and inclined walls. Face better less than 8 degrees are basically vertical walls, and inclined walls face better greater than 8 degrees with vertical. As shown in this figure, the Terra mesh system is one of the mechanically stabilized earth walls, or let's say the slope. Here, you will find the major 3 components of this reinforced soil slope. One is backfill, reinforcement, and facing. So you will find majority is basically the soil, and let's say 80-90% is soil, and rest is only less than 10% is the facing and the fascia. In case of wall, again, same, you have backfill, reinforcement, and facing. Again, you will find the backfill as the major contribution. Now, these reinforced soil walls can be classified based on their fascia. So there can be a wraparound fascia or soft fascia, stone fascia, what we have just seen, make gabions, and then concrete fascia, typically modular blocks or the segmental concrete panels. In the soft fascia also, there are welded wire mesh panels. In stone fascia, you have welded wire mesh filled with stones. And then, of course, you can have full height concrete facings. So there were systems where you can have full height, one single panel of concrete, and then you connect the reinforcement to that. Based on the reinforcement, so first we classified the wall based on the fascia. Based on the reinforcement, they can be classified into geosynthetics and metallic. Now, the geosynthetics basically are nothing but polymeric material. In this, you have geotextile, geogrids, geostrips, or polymeric strips. The popular ones are polymeric strips and geogrids. They are used for permanent structures. In metallic, of course, again, you have the steel strips or the hexagonal mesh, the mesh which is used for even making of the gabion. You can have the ladder, you can have the triangular anchors or loop anchors. And when it comes to the shapes of and different kinds of material, just this slide I put for you to understand what is the difference between the grid strip. So here you can see this is a woven or knitted geogrid, basically produced by the woven or knitted material, bonded where you bond the strips, extruded when you melt the polymer and you extrude them, or a composite mixing the two materials. Geotextiles, the strips typically polymeric and steel, so polymeric steels dated around 1970s at the same time of the steel strips. Hexagonal mesh, double-twisted hexagonal mesh, and let's say even the ladder. Now, you will find there are different types of materials, that is glass, aramid, polyester, polypropylene, HDPE. I'm referring many materials. You will be confused what's exactly these different materials and how and which material we use where. So basically, the stress strain behavior of the reinforced soil structure will depend on the raw material of the synthetic of the soil reinforcement what you have put. So the popular most one is the polyester. Polyester popular because it has very low creep and moderate elongation, moderate stiffness, and more economical. Compared to HDPE, HDPE has very high elongation, very low stiffness. Polypropylene again little lower than the polyester. Glass, aramid, they are very high stiff material. They are not used in reinforced soil. They are generally used in pavements. The reason for they are using in pavements is basically they have very low elongation. They are brittle material, whereas the reinforced soil there will be some movements. So, and because of the brittle failure, also the glass is avoided in the reinforced soil walls or slopes. The question will be, what are the different codes available? So there are a number of codes available, including the first of its kind was the British code BS 8006, and from there different codes have emerged. Ministry of Road Transport Highways 3100, IRCSP 102, EN 14475, AASHTO or FHWA. This is practiced in America. These two are practiced in India. This is practiced in Europe. This is practiced all over world. AFNOR is a French standard. SANS is a African standard. Again, SANS 207 is exactly similar like BS 8006. IRCSP 102 is more or less mix of BS 8006 and FAWA. Recently, we have come up with a BIS 18591. This code gives you the design aspects of retaining walls, slopes, short reinforced soil walls where you have small space for reinforcement length, ground improvement, bezel reinforcement. This is published in 2024. So in case you are more interested in reinforced soil, you can go through this code. It is freely available to download. You don't have to pay. Just go to the BIS website, create your login, and you can download this standard freely. So when we look at the design of reinforced soil wall, you need to understand what is the height of the structure, let's say panel height or the fascia height. In case of the slope on top, what is the back slope height, what's its inclination, and then what is the loadings coming on top, and then you design. Of course, you can design these structures for the two concepts, so external stability and internal stability. External stability means you consider the whole soil mass as one block and you design for it. And internal stability is checking the stability of each layer. So when we say reinforced soil wall is a block, so the figure A is basically a reinforced soil wall. These dotted lines are the soil reinforcement. This is the fascia, and then you have soil. So we assume this is a one single rigid body. It may slide, it may overturn, it may slip, it may have a bearing failure. So that all these checks, what you do in conventional retaining walls, you need to conduct for the reinforced soil wall. When you design the reinforcement length, it is recommended that the length of reinforcement should be minimum 0.7 times h or 3 meter, where h is the height of the fascia here. This is given in BS 8006, also in FAWA, also in IS 18591. Where L is the effective length of reinforcement and H is the total height of a reinforced wall or a slope. When you have to check for the bearing and tilt, of course, you consider the whole reinforced soil mass as a one body. You calculate the resultant force. RV, you have the lateral force, RH. So with this RV, you can calculate the bearing pressure, RV divided by L minus 2E, whereas L is the reinforcement length. E is your eccentricity, which is coming from your overturning check. And this bearing pressure shall be less than your bearing capacity. The bearing capacity you can calculate using this formula given in IS 6403, which is more or less based on Terzaghis formula. Okay, I will not go in details of this, but that's how you can check for the bearing. For sliding, of course, you need to take a ratio of stabilizing force, that is your RV into tan phi, that is mu tan phi. And the driving force is your horizontal pressure coming from the backside. So that you need to check. Slip circle analysis, of course, here you can use various different modes of, let's say, limit equilibrium methods, including Bishop, Morgenstern-Price, or the method you like. I usually prefer Bishop's method. Seismic design, I will not much deliberate on it. Professor already mentioned. Seismic design is very, very important. And Mono-Okabe method can be followed for this. The details can be studied in FAW or IS code. Now coming to the internal stability analysis, so you consider a wall and then you assume a failure surface. It could be through the reinforced soil mass or partly through reinforced soil mass or beyond. Here we check about, let's say, the compound failure or a wedge failure. So let's assume at the beginning I mentioned about the Coulomb and Rankine. So let's look at the Rankine failure plane, which is at an inclination of 45 minus pi by 2, and these horizontal lines as a reinforcement wherever they cut with the failure surface. The red line is the failure surface. You can check for pull out and rupture. What is pull out? Pull out means you have force applied here, and because of this force application, let me just draw here. Yeah, let's say you have force applied here, and then this is the length of reinforcement which is providing your anchorage. This is not sufficient, then the reinforcement will get pulled out. Or when you have this situation where this P force is applied, you have vertical pressure sigma V, resisting force is tau. When this P is very, very high, compared to its strength of the material itself, then the rupture of the reinforcement will occur. Now, when you design these reinforced soil walls, you may consider a wedge failure, or you may have a slip circle also. Now, when you design these reinforced soil walls, they are designed for, as I said, short time to long time. Long time could be as high as 100 years. These are synthetic materials, especially when polymeric materials are used, and they degrade over a period of time. And in order to consider the effect of these synthetic metals over a period of time in terms of durability, you need to reduce the strength of these materials by certain factors. So reduction factor for creep. So these polymeric material will deform over a period of time because it's a plastic. You have a constant load, it will deform. That's typically called as a creep. Installation damage. So basically, when you have the reinforcement and then you are going to put a soil on top and then you are going to compact it with the roller, there will be some damage happening to this reinforcement. That damage is accounted in the design itself at the beginning stage. That's referred as a reduction factor for installation damage. And then durability. The soil reinforcement is interacting with the soil as well as water and maybe the possible alkaline or acidic condition. So how the durability of this reinforcement will be there for such a long period, that is accounted using the reduction factor for durability. And then finally, what we have a factor of safety. So after all these factors, there could be some uncertainty in the estimation of certain factors, not having the sufficient data, then you can put an additional factor of safety. That's how you get the long-term design strength. Long-term design strength is calculated as ultimate tensile strength. Ultimate tensile strength is nothing but you test the reinforcement in a let's say UTM, and whatever strength you get, that is referred as a T ultimate. And that strength you reduce by all these reduction factors, where you get the long-term design strength. Now, you have seen that the reinforcements are basically two types, steel and polymeric. So steel type of reinforcements are referred as inextensible reinforcement. They don't exhibit much of the deformation. And in that case, the design is considered with a coherent gravity method. In coherent gravity method, you consider failure surface to be biplanar, okay, not a single plane. Whereas in tieback method, you consider a single failure plane, something single wedge. This is for the extensible reinforcements. And then accordingly, you design the length of reinforcement. Of course, apart from that, there is a variation in the state of stress or in the soil. In coherent gravity, you assume that from the top of the wall till 6 meters, you assume the state of stress will be changing from at rest to the active. Whereas in tieback wedge method, which is used for polymeric reinforcement, you assume that the state of stress in the whole height of the wall would be the active state. Apart from this, when you go for internal stability, for example, let's look at a failure wedge at 45 minus 5 by 2, you have different reinforcements, they are getting cut. Okay, so you check each reinforcement for pull out and rupture. And when it comes to the seismic design, as per the seismic design, you calculate the additional force that's typically referred as the dynamic increment, that is due to seismicity. And this dynamic increment is distributed in the reinforcement proportional to their length of reinforcement beyond the failure plane. That is LE divided by summation of LE, LEJ divided by summation of LE. And that TMD is added to a static component, So this is a static component and this is a dynamic component. So combination of this total, you get the total force acting at a reinforcement in the static plus seismic condition, and then you target the factor of safety. Now, as we have seen in the beginning, the reinforcement interacts with the soil through friction, So the importance, and 90% of the part of the reinforced soil wall or system is basically fill. So what are the specifications of fill? The fill shall be free draining granular material, having fines passing through 75 micron less than 15%, The maximum particles shall not be more than 75. Of course, the 75 mm is decided based on the compaction. You shall be able to properly compact. If you go for such a higher particle size, you will damage the reinforcement again very high. The structural fill, when you use in the reinforced soil structure, exactly in contact with the reinforcement, you can limit it to the around 40 mm as the particle size. Plasticity index to be less than 6. You can use the pond ash or fly ash as per IRCS 58 if you have the fly ash availability. Of course, there are different considerations for the metallic and polymeric reinforcement, specifically for the backfill. Typically, when you are talking of the metallic reinforcement, so the factors which can contribute to the corrosion of the reinforcement need to be taken into account. So, for example, the pH of the soil, the chloride, the sulfates, the resistivity, that needs to be followed. So I will not go in all these figures, but you can refer this in the standard. When it comes to the polymeric metal, they are very versatile. They are acceptable typically in the range of pH of 4 to 8 very easily, or sometimes 9. Anything beyond pH 9, you need to have a specific testing. But of course, there are certain reinforcing materials which can be used even in the alkaline situations. Apart from this, I have just made a comparison of various standards in terms of pH, resistivity, organic content, chloride sensor. You will find more or less similar numbers are reported. Of course, when it comes to the steel reinforcement, the pH is 5 to 10, whereas in case of synthetic, it can be 4 to 8, 4 to 9. And then this is the gradation, which is given in IRCSP 102, okay, typically for the particle size. These reinforced soil walls can be simple or complex geometry like back-to-back wall, trapezoidal wall, shored wall, abutment. Abutments means you have a bridge girder directly resting on the wall itself through a bank seat, and you may have a T-head wall also. All these design considerations are covered in BS 8006 as well as the IS code. You can refer them in detail. These retaining walls can be used for roads, highways, railroads, airports, industries, mines, parks, architecture, typically stadiums, residential, commercial development, hydraulic docks, hydraulic works also. So versatile. I want to just show you now some typical drawings of these reinforced soil walls. So you might have seen this kind of walls very commonly in the highways. So here you can see the T-shaped panel, maybe I will just go to the pointer. So you can see a T-shaped panel, concrete panel, and then you have horizontal layers of the reinforcement. This is the plan drawing where the strips are being laid in a zigzag fashion. This is the fascia. This is the typical shape of the panel and how exactly these strips are anchored at the back as well as in the fascia. The panels can have various aesthetic finish, can be different shapes, different looks. They can be customized, Usually these polymeric strips are connected to the fascia with the help of the box, typically referred as a cavity connector, which can be light and heavy based on the tensile strength of the strip being attached, and it requires different accessories like S-clamp for holding these strips, J-hooks, the wooden clamps, I'm just showing you some accessories. So the eye bolt for lifting of the panels, the lifting arrangements, the drainage composite. So you can replace the conventional drainage layer behind the panels using a drainage composite. You can use geotextile between the panels to avoid the flow of the soil from the gaps. In addition to that, these Gabion fascia reinforced soil walls, they are mentioned in the IRCSP 116, where you can see this is IRCSP 102. The facing systems can be concrete panels, the blocks, gabions facing, wraparound, metallic, and other proprietary systems. Apart from this, there are different systems, like we call it a hybrid system. Hybrid system means combination of the steel wire mesh and the synthetic. So we developed this hybrid system in late 90s. And the reason for developing this system was when the height of the structure is crossing, let's say, more than 6 to 8 meter or 10 meter, the plain polymeric materials or plain steel materials, they becomes very, very expensive. So the system of combining the steel mesh and the synthetic. So here you can see this is the Gabion fascia or a green fascia where you are combining the steel mesh with the polymeric geogrids. We call it as a paragrids. The combination really helps in optimizing the cost and the construction. So of course, they are factory made material, very cost effective. They can accommodate very high differential settlements. Of course, there are disadvantages also. Let's say when you talk of only steel mesh, it has moderate strength, but it is complement. Let's say the gap is filled by the high strength synthetic materials. So this is a simple cost comparison that is being put. If you are using a mass gravity wall up to 3-4 meters, it is economical, but beyond that it becomes very expensive. If you use Gabion fascia reinforcement, it can be economical up to certain height. If you use only polymeric reinforcement, this is the line. But if you combine this steel mesh and polymeric, they are very, very cost effective. Another example of the cost effectiveness of these reinforced soil walls, you can refer, this is a document from FHWA. This is the cost in dollar per square meter fascia, and this is the height of wall. So you can see a reinforced concrete wall, the cost is from 2 meter to 12 meter, the highest one. The crib walls, bin walls, this is the cost. This is the MSC metal means steel strips, and MSC geosynthetics. And you can see up to a certain height, they are economical, and then they try to cross the MSC metal. That's where when you combine these steel and polymeric, the cost effectiveness is achieved. When you design these mixed reinforced soil walls, you may design for considering the overall stability and internal stability. If you use only polymeric layers, you will need every layer a polymeric reinforcement, okay, and check the design. Whereas in case if you are combining the steel mesh and the high strength geogrid, then you need to look into the stability again same way, including the static and global. In addition to that, you can look into the local stability provided by the secondary reinforcement, because the steel reinforcement will be secondary and the polymeric reinforcement can be primary, and the spacing between the primary reinforcement can be 0.5 meter to as high as 2.4 meter. I want to show some case studies. So probably instead of showing on the slides, I would just okay, let me go through this. This is the first India's first expressway, Mumbai-Pune expressway, where a lot of cuttings were there and a lot of stones were coming from that cuttings. And these stones were utilized in the Gabion walls. And you can see the Gabion walls. This is the photograph captured around 2004. Konkan Railway, one of the very prestigious projects where there were initially a lot of slides because of the lateritic soil nature. And when the railways tried to install the gabions, because gabions are porous, very high drainage, they found these walls are performing better compared to other systems. These are the gabion walls constructed in Nashik on the river Godavari on the black cotton soil area. A very old structure, 2003. And you can see after 10 years. So this is probably 2013 photograph, and now still also as on date, the walls are performing very well. These are the Gabion retaining walls for railways, stabilizing again very deep cut slopes. No, this is very beautiful architectural project, Smritivan Earthquake Memorial in Bhuj, Gujarat. This was used for the basically collection of the rainwater, and in this you can see the gabions are being used for each different wells in a different fashion. Very beautiful walls being built. This is the first reinforced soil wall project built in India, a concrete panel fascia, T-shape. This was built in around 1988. There is a paper published in IRC also. Here the reinforcement was polymeric strip parallel. This is another reinforced soil wall built with the Gabion fascia. This was on National Highway from Jammu to Kashmir. This is Chenari Nashri Tunnel. Here the Terramesh fascia as per IS code and the geogrids were being used. Very interesting project, 22-meter high retaining wall, which is built in eastern part of the country in Orissa. You can imagine 22-meter complete vertical. This is with the stone fascia and geosynthetic. This is again very tall wall, more than 16 meter. This is project near Madurai. This is very old project, more than let's say around 15 years old. Here the fascia is a concrete panel, and here the steel mesh is being used. Double twisted hexagonal wire mesh is being used. This is a wall of around 18-meter high in the state of Madhya Pradesh. Concrete panels with the strip reinforcement. Overall, these retaining walls are economical, could be 30 to 60%, depend on various conditions, but they are economical. Faster construction, nice appearance with maybe a gabion, maybe concrete fascia. Of course, they are proper tested materials. They can help in proper design. And of course, design of gabion walls is similar as mass gravity walls. In addition of additional internal stability check, and even for the design of reinforced soil wall, they are designed as a conventional retaining walls for external stability. In addition to that, the internal stability checks are performed. So thank you very much for patiently listening me. Now I think it's over to you, Sumit.
Thank you, Dr. Mahajan. It was a very illustrative presentation that we had. So now I would request everyone to type your questions in the chat box, and we can see few questions already there. So also, I am just posting a feedback form link in the chat box. I request everyone to attend that. So moving on, we'll take the question. So we have our first question from Sita Rama Bangar. Question basically it's in two parts. Question is in term of cost for same loading condition, which type of retaining wall is economical? The other question is in term of space requirement, does gabion wall stand better in urban structures?
Sumit, do you want me to answer?
Yeah, Dr. Ratnakar, you can take this, please.
Yeah, in terms of the cost for same loading conditions, of course, as I explained, the mass gravity walls are economical up to 4 to 6 meter, and beyond that, the reinforced soil walls becomes economical. So height is one criteria. Of course, the second criteria would be the cost of stones. In case the cost of stone is very negligible, it is coming from excavation. The gabion walls can even be cheaper for higher heights. But in case the stone cost is very high, in that situation, the reinforced soil wall with concrete fascia can be very economical. Thank you.
Okay. Thank you, sir. We have our next question from Mr. Rajesh KN. Question is, how much is the economical benefit of gabion wall over rubble dry masonry, conventional dry rubble masonry? So, Dr. Rajiv, would you like to take this? So I guess, Doctor, can you take this? I guess, sir, Rajiv, sir, you're not audible if you are trying to speak, sir.
Yes. Am I audible now?
Yes, yes, you are, sir.
Please. What is the question? Can you just repeat once?
Yeah, sure, sir. We have this question from Mr. Rajesh KN. How much is the economical benefit of gabion wall over conventional dry rubble masonry?
Okay, that is a very right question. I will appreciate. So study says that gabion wall is economical, but as compared to rubble masonry, you are saying, or masonry, gravity wall.
Yes, sir.
So cost-wise, there is so far I have seen the studies. Cost-wise, benefit is almost equivalent. Cost-wise benefit not that much significant, but the gable masonry has manifold advantages. Our masonry cavity wall, Gabion wall has manifold advantages. For instance, this Gabion wall is acting as a very good drainage or water percolation dissemination. At the same time, it is giving the retaining action. So that is a very advantageous thing. Nevertheless, it also acts as a gravity wall. It can take large amount of lateral pressure. And sustainable point of view also it is good. The serviceability condition also good. So from that point, my answer will be economical side merit you will not get that much. But on the other side, from the point of view of serviceability and sustainability, it has several merits. The Gabion wall.
Thank you, sir.
Ratnakar sir, please correct me if anything you want to add.
Sir, correct, sir. You said correct.
You are very much linked with the industry, I believe. So your input will be more effective, I understand.
Same, sir. What you said is correct.
Okay, thank you. Thank you, Rajiv sir. So we have our next question from Weasley Pereira. And question is, what are bioengineering techniques for slope protection? Can you share any case study to appreciate the effectiveness of this technique for slope protection? How can these technique achieve climate resilience on green highway projects? So, Dr. Ratnakar, would you like to take this?
Yeah, sure. So there are various bioengineering techniques, and when we say slope protection, so I assume it's about the soil erosion. So when we talk of a soil erosion, there are very good techniques available, like you can use the rolled erosion control products made up of jute or coir or synthetic mats. You can use the stone-filled mattresses on the slopes, or you can have just the turfing or sodding, or you can have even mulching. The case study, of course, we have very nice case study from the south of India where we have protected the embankment of the road with the help of the synthetic mats, as well as one case study from the railways that was for the Northern Railway. It was near Lucknow, Utretia section, where the railway embankment was getting severely eroded because the soil was of a silty nature, non-cohesive nature. So there we have used the hydro seeding, hydro mulching, what you can say, and on top of that, synthetic mats were used. We have done another case study for the railways that was for dedicated freight corridor, where we had used the synthetic mat as well as the jute mat combining with the hydro mulching. And of course, these techniques are very, very effective on the highways. Sometimes I have seen people using the concrete, but I don't consider concrete is a good solution when we talk of a green highway. So I would prefer to stick to these bioengineering techniques. Thank you.
So,
Yes,
thank you, Dr. Mahajan, for the question. So we have our next question from Mr. Himansh Kumar, and the question is, how much height we can achieve building retaining wall structure? So, Dr. Rajiv, would you like to take this?
Yes, definitely. So the conventional rigid retaining walls, I think height is up to, I think 10 meter is the conventional height generally. This retaining walls, I mean cantilever retaining wall maximum go up to, we are designing 10-12 meters.
Okay.
And for
Thank you.
these
Yeah.
flexible retaining walls, I think quite higher than these rigid retaining walls can go long.
Okay. Thank you, Dr. Rajiv. So for the answer. So we have our next question from Koti Veera Raghava, and the question is, when is using RE wall is the minor cracker appearing at the end of the friction slab of DBM layer? What is the reason for it? Please explain.
Okay. Okay, I will take this question. Is okay.
Yeah, Dr. Ratnakar, please.
So typically when you see the DBM layer cracking at the edge of the friction slab, so typically the compaction behind the fascia panel is very, very critical. And when you compact the soil, it is recommended to use the 10-ton vibratory roller, okay, for soil compaction, except the portion near fascia. So around 1.5 meter from the fascia, you need to use the light compactor. So in case the soil is not really compacted, usually will be the case near the fascia, because many times I have seen people are not using the proper compactor and not achieving the density. And after maybe a couple of seasons, then you see the settlements of that 1.5 to 2 meter. Because if you see the friction slab, typically the dimension of the friction slab is 1.8 to 2 meter, which is exactly coinciding with this 1.5 meter. And there you start observing the cracks. So one is the soil compaction. Another issue what I observed in a couple of projects is the drainage. Sometimes the water is seeping from median and not being taken care by proper protection. There are issues with the intrusion of the water, and the soil fines getting washed from the fascia itself. That's also the second reason.
Okay. Thank you, Dr. Mahajan. So we have another question, which is, do the HDPE gabions get deteriorated in salt or acidic water? So Dr. Saha or Dr. Mahajan?
I think Mahajan sir
Maybe.
can better.
Yeah. So HDPE gabions. So very good question. What I would say, HDPE gabions, they don't have issue with the salt, but most important part is HDPE is a polymeric material and it will degrade over a period of time when it is exposed to the environmental conditions, typically UV rays. So HDPE will not have any issues related to the salt, but yes, it will degrade if it is exposed to sunlight.
Okay. Thank you. So we have our next question. In construction of retaining wall against the rock or cut hill, the pressure acting on the wall is limited only to the backfill between the wall and rock mass, or it include the rock mass also. So, Dr. Saha?
Yes. What is the question? Sorry.
Yeah. Question is, in construction of retaining wall against the rock or cut hill, the pressure acting on the wall is limited only to the backfill between wall and rock mass, or it include rock mass also?
Yeah, it's a very good question, brother. Yes. You see, actually, we are generally conventionally backfill material pressure we are calculating. The concept is that the critical wedge, the retaining wall we are designing the wedge. The formation of the wedge depends on the backfill material characteristics. Now, the wedge consideration is an important factor. It varies from one school of thought to another school of thought. Now, if the rock mass is coming, intersecting within this wedge, we should also consider the rock mass properties calculating the pressure. Am I understandable? Yes. Am I clear?
Yes, sir. So thank you, sir. Thank you for the answer. So with this, we have come to the end of the session. Due to paucity of time, we'll take these many questions only, and we'll be reverting you over the email. So we thank you everyone for your presence in our webinar, and we hope that you found this session informative and it was fruitful for you as it was for us. Thank you all. Thank you for participating.
Thank you from our side also.
Thank you, Dr. Ratnakar Mahajan and Dr. Rajiv Saha, for your time. So we were able to have this very informative session. So, and we will be continuing this webinar series, and we'll be having 4 more webinar in this series. Thank you.
Very
Thank
good.
you all.
All the best for the next seminars. Thank you, Institute of Engineers and McAfee for organizing such informative seminar where we can learn, and not but the least, our learned audience, presence of learned audience. So with this, from my side, best wishes for the next ones. Thank you, Ratnakar sir, for giving me this opportunity to interact.
Thank you, sir. Thank you, Institute of Engineers. Thank you to the audience. Look forward to see you in next webinar. Please do fill the feedback form, which must have been shared by the organizers. Thank you.
Yeah.
Sumit, with your permission, can we end the session?
Yes, sir. Sir, I just wanted to know, is there any feasibility that we can have this link in the chat box?
Let me check with my team and I will get back to you
Yeah.
on
No
this.
worries, sir.
Or
Good day.
what we'll do is we can send to all the registered participants this link separately
Yeah,
by
yeah,
mail,
sir. Can be
bulk
done.
mail.
Yeah.
And for the next webinar, we will come up prepared for this option as well.
Sure, sure, sure. Okay, sir.
Okay.
Thank you.
Very well.
Thank you very much. Bye.